Hello, my name is Miranda Williams, and I'm going to be going through my Physics 2211 Lab 1 procedure, and the procedure was over the constant velocity. So the purpose of this procedure is to observe an object moving at a constant velocity without changing direction. We compare the observed position of the object to the computational model based off the movement of the object. The key principles that were used within this experiment was Newton's first law, Newton's second law, and the constant velocity. So Newton's first law is an object that will remain at rest or remain in motion unless acted upon by an external force. Newton's second law states that the change of the motion of an object is proportional to the force impressed and is made in the direction of a straight line in which the force was impressed. The constant velocity is no acceleration due to Newton's second law. Here are the graphs. So the first two graphs are the observed model of the marker rolling across the table. And then the computational model is on the far right and shows the predicted course of the marker rolling across the table. So here we have four formulas. We have Newton's second law, we have the position update formula, we have the average velocity formula, and finally we have the velocity update formula. The Newton's second law formula was used to confirm that our velocity was constant, and we have the position update formula and we have the velocity update formula because we use those in our model of our computational system on GlowScript. And then the average velocity is just the velocity over time. So the system and the surroundings of the experiment. So the system of the experiment was the expo marker that the force was applied to, and then the surrounding of the experiment was the hand that was used to apply the force to the expo marker to roll it across the table. To begin our experiment, what my group did is we set down a metric ruler so we could scale the experiment, and then we also included an expo marker. So we laid the expo marker on the desk and we used our hand to push the marker across the table and have a constant velocity. And while that was happening, somebody was recording the video. So then we have the video and we use Tracker and we use the calibration stick within Tracker to calibrate the different points of where the marker was going through the video. And from there, we created graphs based on the movement of the marker at different positions of time. Next, we then went to GlowScript and we had a starter code that was given to us, and then within the starter code we added Newton's second law so we could track the marker and its movement across the table over the time interval of the video. So these are the initial conditions, the ball velocity and the ball position within our experiment. You may have seen this slide before, but these are the results of our experiment. So these are the observed models of our system that we set up. And of course, we have the computational model right next to the right of it. So there are some key differences, of course, with the observed model. The velocity is not as constant as the computational model shows. So the reason for the differences between the observed graph and the computational graph can be linked to error within the experiment. So within the experiment, the sources of error can be the applied force. So whenever you're applying the force to the expo marker, maybe when we did apply the force to it, we applied it at different parts of the expo marker. So maybe one half was rolling one way and the other half wasn't rolling as much just because the difference in applied force. And then also with the applied force is that it may have been too hard and led to acceleration of the expo marker, so then the velocity wasn't as constant as it needed to be. And then the last thing would be the friction from the table. It might not have been as much of a smooth surface as we needed, so then the friction also counteracted against the constant velocity that we're trying to observe.